Hello, this is Statistics, Section 3B. Last time we were talking about how to deal with an OR situation, how we have to be careful of mutual exclusivity, if it overlaps, if it doesn't overlap. So this time we're going to add into that an AND situation. So you want this and this to occur. Now when you have an AND situation where you have two specifications, you have to be careful on whether or not they are independent. So it's kind of a similar idea about overlappingness, and it kind of affects the the probability of something occurring. So if you have an independent situation where there's no sort of overlap, nothing of one something happening in one does not affect something happening in the other, then to find the probability of this and this, you just find the probability of each and multiply them together, because then it's that much less likely. So multiplication of a fraction becomes an even smaller fraction. So if you do have a dependent situation where one is going to affect the other one occurring, then you have to take that into account. So instead of just multiplying, you multiply by this symbol right here, which is called F given E. So right here, this straight line, kind of like an absolute value bar straight line, it says that the first one is what you want to occur, the probability of F, and then this is read as given, and then it's saying that E has occurred already, so that has been given. So again, don't worry too much about the formulas. Don't get overwhelmed or nervous about these, because it's one of those things that you just kind of reason through. So it makes sense when you see these examples. So first off, let's decide what would be an independent versus dependent event. So this one, studying for your math exam and then making an A on your math exam. So the probability of studying compared to the probability of making an A, does one affect the other? Well, we would hope so, right, in a math class. If not, then you probably don't have a very good study habit. So this one would be an example of a dependent situation. Okay. And then the next one, we have the two situations where Chris checks out a book from the library and then Jessica wins the state lottery. So she just won that big Mega Millions. So these would probably be unrelated events. Chris checking out the book probably did not affect Jessica's probability of winning, unless his book was specifically how to win the lottery, which I don't know if that book exists. So we would consider these to be independent events. Okay. So let's look at some more practical applications. Now, first off, if we just had just kind of raw numbers without the story involved. So it says the probability that event A occurs is 0.51, 51%. Probability that event B occurs is 44%. And it says that we already know that the probability that both A and B occur is only 5%. So that means A has occurred and B has occurred. They are dependent events. Now it's asking us what is the probability of B occurring given that A has already occurred. So looking back here, using this as kind of a formula, you can see here's the probability of this and that equals this times that. So in our situation, we have this probability and we have this probability, but this time we are asked to find the probability of this given that. So just like in any algebra problem, if you knew x equals y times z, and you wanted to know z, you would just divide by y. So we can find that missing unknown right there by dividing by the one we didn't know. So we're actually going to take the probability of A and B, 0.05. We know that that's going to be the probability of, now here's where you got to be careful, which letter. So look back at our formula here. So notice that this right here matches the one in the back, E. So the F is kind of in the middle. So the probability that E occurs times the probability of F given E. This one, it just switched the letters. Probability of F occurs given times probability of E given F. So notice that the matching ones are on opposite ends. The F is in the middle. Okay, so knowing that, the opposite ends, this one I need the A, the probability of A, times the probability of B given A. So I have to be careful. I can't multiply by the probability of B. That's not the same thing. So let's go and write it out in symbols first, and then we'll come back and do those numbers. So this is the probability of A and B. Okay. So this time we know the probability of A and B is 0.05. we know the probability of A is 0.51, and we're looking for the probability of B given A because they asked us to find that specifically. So just like any algebra problem, to find the unknown, we divide both sides. So I'm a little bit out of order here, trying to kind of write this in the space. But basically we have to divide by that 0.51 because we're going to have to cancel it there on the right. And then as always in algebra, we have to do the same thing to both sides, which means our final answer for the probability of B given A is, hang on, I have it written down, a crazy long decimal of 0.098 blah, 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 blah. Okay. So we went a little out of order there, we're just filling in the space. So we started here and then over here we continued to this answer. Okay. So this next one, sorry, there we go. Okay. We have the probability of A. Now right here, notice there's a bar over it. This is important. The probability of not A. The probability of B given A. They said this time they are dependent. Okay, that's just like last time. This time we're going to find the probability of A and B. Okay, so they gave us this one, and they gave us what it looked like we needed in the formula, but that bar right there is important. So that bar is actually another way to write the complement. So remember that complement we learned here. There's a few different ways to write it. So this one, they showed it with kind of an apostrophe. That is one way to denote a complement. And then another one is to put a bar over it, just like we saw right there. So the probability of E with a bar over it. So just two different ways to write the same thing. So this is another one of those examples where statistics is kind of one of the least consistent math classes. We're not even agreed on our symbols, so we kind of have to really watch out when we're communicating. Okay, so in this one they said the probability that A does not occur is 40%. So remember that it always adds up to 100%. So if A did not occur 40% of the time, then A did occur the other 60%. So that means I would need to do the 1 minus 40% is 60% is the probability that A did occur. Okay, so this is the piece of information I needed because the probability of A and B is going to be, sorry, this one because they are dependent, the probability of A times the probability of B given A. Okay, let's write that down. So the probability of A and B is going to be equal to the probability that A occurs times the probability that B occurs given that A has already occurred. Okay, so this time they gave us this one. He was 0.9. We were able to decipher this one. They tried to trick us, but we got it as 0.6. So this time there's no algebra involved. We just multiply. So the probability of A and B is, drum roll, 0.54. So these are, like I said, just kind of generic, using the symbols, kind of interpreting that formula there. But like I said, a lot of times it should just kind of make sense. So here we actually have kind of the story to go with it, the context. So it says that 56% of all the town's residents own a dog, 70% own a cat. Of the dog owners, 48% also own a cat. Okay, if a town resident is chosen at random, we're going to find the probability that they own a dog. That could be own a dog and a cat, but they do own a dog for sure. The probability they own a cat and a dog, and then the probability that they own a dog given that they have a cat. So you can see in this situation what's going on, what this given kind of really means, because we know some people have just dogs, some people have cats and dogs, some people have just cats. And you can see from these percentages here that I couldn't just like add these up, because of course 70 plus 56% would go over 100%. And that's because some of those percents combine. Some people have the dog and the cat. So these things right here help us to see that it's not always as clear as what you would expect. So the probability that someone just owns a dog, whether they own a dog and a cat or just a dog, that was actually given as the 56%. Okay, so right here when they told us this information, that wasn't exclusively just a dog, it was having a dog, period. So then the probability that they do own a dog and a cat, okay? Now this time we need a little bit more information. Okay, so if they told us that 56% own dogs, let's kind of look at it in a Venn diagram here. We'll color code it. 70% own cats. Okay, we know that some people own just the dog, some people own just the cat, and sometimes they overlap there. Okay. So the probability, we have to use this right here, this 48%. The probability that a person owns a dog, wait, of the dog owners also own a cat. Okay, this isn't the same thing. I know it seems like it should be. Of the dog owners, here it is. Here's where we have to interpret. So of the dog owners, this one is the dog owners. They already, for sure, have a dog. 48% also own a cat. So this would be the probability that somebody owns a cat given that they already have a dog. So here's how you would phrase this seemingly, new terminology. Of the dog owners, 100%, they've got a dog, given that they have a dog. 48% also own a cat. So the probability of cat given dog is 48%. Here we go. All right, so the probability that you own a cat and a dog, we now have enough information because we just found that the probability of cat given dog is 48%. So that means to find the and situation here, I would need to multiply by the probability of dog. Because remember, it's always the one on the outside, the dog's right there, so cat in the middle. So this one we know was 56%. This one we know was 48%, which means the multiplication there is about 26, almost 27%. So if we use this Venn diagram here, we know that the purple, the cat owners, is 70%, but we just mathematically found that 26, almost 27% own both. I don't know why I can't get that to go away. Okay, so that means the other, how many? 70 minus 27. The other 43% own just a cat. And then of course 56 had dogs. Well, 56 minus the 27 is 29%. So now we've been able to discover how many people just have dogs, how many people just have cats, and how many people have both from this formula right here, from this statement. All right, so now it asks us to flip it. So it says, what's the probability that somebody owns a dog given that they own a cat? So here we go. The probability that they own a dog given that they own a cat is going to be written like this: dog given cat. So it's not going to be 48%. It seems like it should be, right? But it's not always the same. Just like you can see that this 43 is bigger than this 29. So it kind of seemed like it should have been even, but it's not. Okay, so the probability of dog given cat, we have to go backwards just like we did up here in the purple one. So we're going to have to take the probability, let me scoot this over. Okay, the probability of cat and dog, no, my writing's kind of messy there, cat and dog, sorry, times, nope, this one was the probability of cat. There we go. So here's our formula. So the probability of cat and dog, where we have this statement that we wanted instead of this statement where we were given, needs a probability of cat multiplied to it. So this time I'm going to put in what I know. This is what I know from the last one was 26, almost 27%. This is one of the pieces that was given. That was the 70%, the people that own cats. So not just cats, just any cat. And then I'm able to algebraically find the piece of information that I didn't already know, the probability of dog given cat. So I take my 0.2688 divided by 0.70, and that gives me, let me show that step, 0.70, just so you have it. And then we get 0.384. So just like I said, it's not 48. It seems like it should have been, but it's not the same. So the probability that somebody owns a dog, given that they have a cat, is actually slightly less. And this is because more people have cats total, and in fact, more people had only cats. This 43 was bigger, this 70 was bigger, so it's a little bit more likely that they also had a cat than it was that they also had a dog, because dogs were slightly less likely in this town. So here we go. Okay, now one of the more common places that you see this, this given situation is in card problems. So this one we have a card drawn with replacement from a standard deck. And if you remember when we had that card problem in the very first slide, I talked about whether or not we replaced it. There's all these little things to watch for. So right here, here's one of those keywords you want to underline, you want to really watch out for, with replacement. So it says that means that they drew a card, they looked at it, they put it back. Okay, the card's back in the deck again. What is the probability that the first card is a heart, the second card is red, and the third card is a face card? So the probability that the first card is a heart. If you remember from our last video, we decided there were 13 hearts total in the 52 deck card, which also reduces to 1/4. Okay, let me see if I can put them side by side there. Okay, so 13 out of 52, which is also 1/4 of the deck. Okay, so whichever way you thought about it. Then it says the probability that this, and this happen, keyword and. So that means we're going to multiply, okay? If it was an or, we would add them, and is multiply. So when a first card is a heart, the second card is a red. So how much of the deck is red? That is half of the deck, or 26 out of 52. And you'll see in the next problem why I'm writing it out in this weird way. And then the third one is a face card. So remember that was the jacks, the queens, and the kings, but there was one in each suit. So that's 3 times 4. There were 12 face cards. Sorry, 52. And that actually reduces as well. To 3/13. But that one is less obvious. But just for consistency, I'm going to put their reduced fractions down there. So then when I multiply 1/4 times 1/2 times 3/13, I can do my math inner to get a fraction, which remember is always preferred just because they are exact. But this is kind of one of the scenarios where 3/104 is not as relatable. So this would be a situation where we usually in real life would kind of go more with a decimal because we think of it more along the lines of a percent. So I still always like fractions because they are exact. I can check your work a little more easily and give you partial credit. But in this situation in real life, you probably would have put the answer of 2.8 or almost 3%. Okay, so that is the likelihood that this situation occurs. All right, so the reason I wrote it out all weird like that, sorry, my notebook's messing up. There we go. Is because here's that almost same problem, but this time they drew without replacement. Okay, so what that means is they took the card, they looked at it and they kept it in their hand. So now the deck is smaller. Okay, so they started with 52 cards. What's the probability that the first card they drew was a jack and they're now holding a jack? Well, there are 4 jacks in the deck. You might say that's 1/13 of the deck, but here's why I showed it both ways last time. Because now they're holding one of the cards. Without replacement, they draw a queen. So what's the probability that the next card they draw is a queen? Well, there are 4 queens in the deck, but now there's only 51 cards sitting there. So it slightly affects the next probability. So this is that technical probability of B given A. Since one card has been drawn, this fraction has been affected. This is the probability of a queen given that one card is drawn. There's only 51 cards. So that's why we don't always think of it in that formula form, other than these questions specifically where they're in formula form. So that's why I showed you both ways, so that it made a little bit more easy transition here. And that again gives you a weird fraction, but when you change it to a decimal, that more relatable decimal in this case, you can see that it is a very unlikely scenario. It is actually less than 1%, it is 0.006. Okay, so 0.6% chance that this is gonna happen, pretty unlikely. And this is how all of those casinos make their money. They make up these situations which are very unlikely, and then you put money against it, and then you lose all your money. So one last example, what if I'd wanted to get a jack and another jack? So same situation, same deck, but I wanted a jack and then another jack. Okay, then I would have had that 4 out of 52 for the first jack. Sorry. And then my next card, I have 51, just like the last one, but this time I'm holding one of the jacks. So there's only 3 jacks in the deck. So my probability of getting another jack, given that I'm already holding one, is 3 out of 51. This reduces to the fraction of 1/221. Okay, so it's actually slightly less likely. All right, so a lot of times we'll deal with card games like that. Here's another situation where a given situation could occur. We have this jar of coins. So it says, what's the probability we reach in the jar, we grab a quarter, hold it in our hands, and then grab a nickel? Well, first off, we need to see how many coins are in the jar. So we dump it out, we count all the coins, and we decide there are 83 coins total. I'm adding up all those numbers. Okay, so the probability of reaching in the jar and grabbing a quarter, just that much, careful, it's not 25, it's tempting to say quarter is 25. There were 7 quarters out of 83 coins. And so they want this to occur too, so we're going to multiply. They want to reach in that same jar that is now 1 less quarter, only 82 coins in it, and grab a nickel. Well, since we just grabbed a quarter, there's still 24 nickels. Okay, and then we figure that up. And technically, it's the fraction 84 over 3,403. Now, more than likely, your calculator is not going to math enter a fraction like that for you. So what I did to get that, if you're following along, is I did 7 times 24, and I did the 83 times 82. And then sometimes you can reduce the other way. But this is another one of those situations where you probably would have put the decimal answer there. So 84 over 3403 is the crazy little decimal of 0.02468. Now, if you are doing decimals, it's always a good idea to make a bunch of decimal places. General practice, put at least 4 decimals. If they haven't specified that they only want 2, put at least 4. So that's just kind of general practice. Okay. So bonus extra example, what if they wanted to grab 3 quarters? Okay. then the first coin would have had 7 out of 83 chances to be quarter. The next one would have had only 6 because we're holding one of those quarters. There was only 82 in the jar, which means, of course, our third grab in the jar, there was only 5 more quarters to choose from, and now there was only 81 coins in the jar. So this gives you a very, very slim chance of 0.0003809. Okay, or a crazy little fraction, just in case you're curious, it would be 35 out of 91,881. Okay, all right, so bingo balls here. So they've got 5 red balls and 3 yellow balls all hanging out in a box. It says we're going to draw 2 balls from the box without replacement. So again, we're holding them in our hand. What is the probability that 1 ball of each coloring is selected? So this is sneaky. They didn't say red then yellow, yellow then red. They said 1 of each. So we have to be careful here because we have a few different scenarios. They would have been happy if we drew a red and then drew a yellow, or they also would have been happy if we drew a yellow and then drew a red. So this is actually a scenario where we have and or in the same problem, because we could have had red and yellow or yellow and red. So we have to break this down. So the probability that they drew a red ball first, there were 5 reds out of 8 balls. Then, after drawing the red, they drew a yellow. There are still 3 yellows, but now there are 7 balls. The probability that they drew yellow first, 3 out of 8, followed by red, 5 out of 7, would be this right here. Since they were happy with this or that, the probability of this and the probability of this are both satisfactory. So I add the 2 probabilities together. So remember, in OR situation, we add them together because both probabilities are acceptable. So that's going to give us, they actually both come out to the same 15 over 56. And when you add 2 15 over 56s together, you get 15 over 28, because it does reduce. Or if you take that as a fraction to a decimal, you get 53.57%. So it's actually relatively likely because there weren't that many balls in there and they were almost split 50-50. All right, Mr. Fraga's physics class has 122 students. He broke them down by academic year and then male versus female. So looking at this breakdown of his students, what is the probability that she, has everybody in the room, shuts her eyes, runs in, and grabs someone by the hand, that she is selected a male student, given that she randomly only chose from the juniors? Okay, let's write this as a statement. The probability that the student she chose was a male, given that they were all juniors. So she's already split them up. It's a room full of juniors, that's given. The probability that she grabbed a male by the hand, just choosing randomly. Okay, so this one means we need the male juniors, 18 right here, but it's not out of all 122, it's out of just the juniors. So if you look at just the juniors, there were 28 juniors. Okay, so what we did here is we found the probability of male juniors, male and junior, divided by the probability of juniors. And that gave us this right here. So we were following the formula, but notice how we don't really think of it as a formula. Okay, now what about if she chooses a junior, given that she's already decided they're males? So this time she's separated a room full of all the guys, and she closes her eyes and says, you come here, and that person happened to be a junior. So this time we need the total number of male students. So we add these up, there were 59 male students, and she closes her eyes and says, hey, you come here. That person is a junior. Okay, so this time, here's our male juniors again, same 18. but it's out of all 59 boy students. Okay, see how it makes a difference. The order is important. All right, so last one. Here we've got a coin. It gets tossed 9 times. What is the probability that it's all heads? And then last, we're going to find the probability of getting at least 1 heads. So for this problem, think back to our very first one here. So I was trying to kind of subtly show you this pattern. When there was 1 coin, we had how many options? We had 2. When there were 2 coins, we had 4 options. And when there were 3 coins, we had and we ended up with 2 options. Here we had 2 coins, we had 4 options, and here we had 3 coins and had 8 options. So do you notice any kind of pattern? I'll give you a hint. If we had 4 coins, we would have had 16 options. Notice how it doubled. So what happens is that we had the options themselves, heads, tails, to the power of how many times it got flipped. So this one we had 2 to the first, this one we had 2 squared, and this one we had 2 cubed. Because every time it doubled, we had that many more options. So the reason that I point out this pattern is because now it's going to be much easier to handle a coin that is tossed 9 times. Instead of having to write out heads, 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 tails, tails, all those crazy options, which would be a lot of them, we know that it's really just going to be 2 to the 9th power, just like our other problem. So 2 to the 9th power is quite large. It is 512, so we probably wouldn't have wanted to sit there and draw out all 512 options. Okay, so the probability that you get all heads in those 512 options. Back up here at our first example again. In the green one, we had heads or we had tails, right? So the probability that it was all heads, there's one case. Here we had 2 coins going on, but how many times did we get all heads? Just the 1. Here we had all these options here, but how many times did we get all heads? Just the once. There's only one way that we could have flipped it and got heads every time. So the other one we kind of said, okay, the tails might have been here, 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 the heads might have been here, here, and here, but to get all the same, there was just that one case. So right here, if we flip the coin 9 times, even though you look at all 512 heads and tails mixtures there, there's only one way that it could have been all heads. 1 out of all 512 options. Okay, so the probability that you get at least 1 heads. So that means it could have been 1 heads like these guys. It could have been 2 heads like these cases, or it could have even had all 3 heads. It just said at least 1. So of these purple ones, the only case that didn't have at least 1 heads was this guy. Looking over here at these 4 cases, here's the case of 1 heads and or 2 heads. So again, the only case that it didn't have at least 1 heads was all tails. So you can see here, even if we had all 512 drawn out, the only time there wouldn't have been at least 1 heads would have been the case of all tails. So if I had all 9 tails, that's the one and only way I wouldn't have gotten at least 1 heads. So that means if I found the complement, that would be much easier, right? Because the probability of getting all tails was 1 out of 512, just like all heads. So the probability of not happening would be 1 minus that. So it would be all other 511 options. So the one and only way we wouldn't have gotten at least 1 heads is if we got all 9 tails. All right, so that's section B there. Hopefully this has been helpful. Let me know anytime you have questions.